Oh, you
Yeah.
got a one that wasn't designed then for the Hospital? Oh, it should. Oh well, let me find out. I don't know.
I thought if I just did it twice, it would work. You know,
It might be.
but it
That's what
doesn't. It
my
just
gut
gets,
feeling is.
yeah, well, mine too, but it just got more and more complicated. It was just ridiculous.
Well, because it is trig, there might be a trig identity issue going on as well.
There is, but I didn't know if I could do 3x, 2x, like take a 3x, turn it into a 2x at an x or something. I was confused with that.
Well, let me find out. Let's take it one step at a time and see what happens. You get 3. You differentiate this guy, you get 3 cosine and 3x. That guy, you get take away and you get 3 secant squared 3x. Okay, let's check that. If you plug in 0, yep, 0, so it's still, I might come back to that, but let me try L'Hopital again. So if I do L'Hopital one more time, this fella becomes -9, because you get an extra 3.
Yeah.
And you get a sine of 3x, and it becomes positive, so it's positive. If you differentiate -3 sine squared x, that's interesting. So what's that?
That's really a problem.
-3 secant x squared. So
Yeah.
you're going to get -6 secant x, and then the derivative of secant x is secant tan x. So you're going to get that, and I suddenly lost my 3x's. There we go. Oh.
Well, I thought you had to do the product rule because it's secant squared.
Yeah, you could, or you could do a chain rule. You get the same result.
All right, well.
It wouldn't matter. You would, if you did it properly, you'd get the same result. So what is this going to be? Okay. I have the sine of 3x.
Is it supposed to be secant
over.
squared 3x, not just x? Or is it just x?
It's this thing in the bottom is -6 secant squared dx tan of 3x. Keep wanting to lose my 3x's.
Okay.
Because what you do is you multiply by 2,
Mhm.
reduce that power by 1,
Mhm.
and then the derivative of secant gets you another secant back with the tan. So what I'm doing here is seeing if I can see an identity for it. A secant squared is 1 over cos squared. A tangent is a sine over cosine. So I'm looking at 9 sine 3x over -6 the sine of 3x all over cos cubed 3x. Well, a fraction becomes its reciprocal. So you've got 9 sine 3x followed by a cos cubed 3x. There you go. That's how you kill it. So you get -3 over 2 cos cubed 3x, which gets you 1. So -3 over 2 is the answer. So it was a trig identity. We had to figure a better way of writing that guy.
Back up where you circled that -3 sine x squared. That isn't that supposed to be secant 3x squared?
I don't know. Oh, the up here? Yes. I keep, for some reason, I just keep losing my 3. So every time you say an x, pretend I've written 3x because I should have.
And did you remember to do it then down here where you have -6 secant squared? I had to do another, when you do the derivative of secant 3x, it's going to have an extra 3. Did you do that? Where you have -6.
Oh, did I do the other 3?
Yeah, because I kept doing
gotcha.
that.
Yes, I don't think I did.
I know.
I didn't, did I? Right, so if you do this guy, you're going to get a -6. You're going to get a secant 3x. And because I lost the 3x, I forgot about that. And the derivative of that does get you another 3. So you are going to get 18 of them.
Yeah.
It's 3 times 6. So that's going to be 18.
Nine, 18. That's what I got.
18.
And
Yeah,
18. Now, negative
I
a half.
tried 1/2. Okay, maybe I didn't do the stinking
No,
sign
not
right.
1/2. Negative 1/2.
Yes, I know.
Negative 1/2.
Maybe I forgot the negative on mine because I did try
Maybe.
1/2 once. I don't know if I have very many chances.
Because I did. Well,
All right. Well,
that's my my third version.
and you did do the
It was
top.
a trig identity, but I'd lost the 3.
And you did the top. Once you do the top with the La Hospital, it looks like you can just leave the top and just work on the bottom. Is that true?
Yes.
I
Well,
thought
there
you had to do
wasn't
both
anything
top
I
and
could
bottom.
do. Are you doing La Hospital? Yes.
So we stopped and
That's
didn't do
not
the
what I
top.
thought you were asking. Well, I didn't do the La Hospital in the bottom. All I did is I rearranged this so I could see if I could turn this bottom into something else.
Into something else. Okay.
So I'm not doing from here to here is not La Hospital. From here to here is just the same function, but expressed in a different form
In a different
to
form.
see if
Okay.
I can find an identity to solve it.
All right. Good. That's what.
Good
Okay.
grief.
What was that,
Try to make-
Maggie?
What?
Did it work for you, Maggie? Did you get the right answer now?
I just copied your work. Mine has different
Okay.
numbers though, so
Oh,
I'm pretty sure
Okay.
it'll just be the same thing except with the other numbers.
gotcha. So keep an eye open because I did drop a 3 in case I dropped another 3 somewhere else. I can't see it right now, but if I had time, I'd look at it carefully and find out.
Thank you.
You're welcome.
Yes, thank you so much.
La Hopitals are not meant to cycle forever. So if you start seeing that, you probably should stop doing La Hopital and just see, well, for trig identities. Most of the other times when it's just powers, you can kind of see where the thing's going. And sometimes you have to use the just because you can doesn't mean you should rule. Some questions are best left away. Don't do L'Hopital on them. Things with lots of square roots, do the conjugate method. Because square roots don't behave well when you differentiate them. They get ugly really fast. And in some, they could repeat themselves forever. Okay, here's Craig coming in.
I have an update about my interview that happened last week, if anyone would be interested.
We are very interested, especially if you give me money at the end. So go for it.
Let's see. I got a phone call yesterday and I was offered 3 different positions on the student activities board here at Olympic College. So I have to choose what I want, but the update is that I was offered 3 different jobs and I get to choose what I want.
It's pretty good.
Congratulations.
Yeah,
Thank you.
I've
Excited.
never been offered 3 different positions.
Me
Oh,
either.
I'm jealous. They must like you.
I was genuinely shocked. I did not expect it. And I thought I didn't get an email on Tuesday about a secondary interview. And so I kind of thought that I wasn't going to be getting a
That was
job.
it
I
then.
thought. Yeah. But then she called yesterday and I'm very excited. So yeah, that's my update.
So do you know which one you're going to be doing? Have you decided that yet?
So I was offered the student coordinator for the Shelton campus. I was offered the entertainment and traditions coordinator and another position that I don't remember because the 2 that excited me were the Shelton campus and event entertainment and traditions. But the Shelton campus is over an hour commute each way.
Yeah.
So that's
If you
over
lived
2 hours.
in that direction, yeah.
Yeah, so that's over 2 hours
And
a day
this,
commute.
and thank you, winter.
Yeah, and
It's
winter
it's
and
pretty, it's
thinking
a
about,
nice drive in the summer.
I have to keep my grades at a certain level to keep the job, and losing that much time to a commute might not be the wisest. So I think that I'm going with entertainment and traditions. I have to call and let her know today.
Well, I have, I'll tell you my news, but I've probably already told you. Me and my wife have booked our Vegas trip. So we're going at the end of August. My life is very boring. That's about all I could tell you that's even vaguely interesting. But
Hey,
boring is good.
Vacation's a good time.
Hmm?
Vacation
Vacations
is
are
a
good,
great
yes.
time.
So if any of you are in Vegas at the end of August, you didn't see me, you don't know who I am, and what's that? What stays in Vegas thing?
It stays in,
So
what happens in Vegas stays in Vegas. Yeah.
yeah, pretty much. That's the phrase I was looking for. So that's what I'm going for anyway. Well, let's get started. Good morning, everyone. And we're on our last section. We're going to be doing antiderivatives today, and I'm pretty sure tomorrow. And but we'll finish before the end of tomorrow, because tomorrow we're talking about your test 5. And I also want to spend a little bit of time tomorrow talking about what you need to get in the final to pass, to get a 4.0, whatever your goal is. So what is the last section about? It's on a topic, a process called finding an antiderivative of a function. I'll just read this out. The process of finding the antiderivative of some function y equals f of x is to find another function called y equals capital F of x, and this other function, capital F of x, has the property that its derivative is the original function. Sounds very cyclic, but think of it like this. If I tell you what the derivative of a function is, can you work backwards and tell me what the original function would have to be to get that derivative? So right now, you normally get a function and you find its derivative. Can you think, I'm telling you the derivative, can you work backwards and find the original function? And we are going to find antiderivatives of polynomials, radicals, rationals, exponentials, and trig functions. And tomorrow, perhaps some of these tomorrow as well, we're also going to use this process of antiderivative to solve some questions like, how do you find the position function if I tell you the velocity at time t? And how do you find the position function if I tell you the acceleration? So these would be applications of doing the antiderivative. So let me work it like this. Suppose I tell you that the derivative of a function was 6x squared. Well, in fact, let me change the notation. I'm going to put the function here and its antiderivative here. And the reason why I changed my notation is to be more consistent with what we're saying. Right. So suppose I tell you right here that you have 6x squared. So if I said the derivative is 6x squared, who would be the original function, right? That's the antiderivative process. Suppose I told you that it was 4x. Suppose I told you it was negative 10. Now I'm going to give you the answers to each of these. This guy here is 2x squared. This guy here is 2x, and this guy here is negative 10x. So this one, 2x cubed, this one, 2x squared, this one, negative 10x. Can anybody see a pattern? Because we don't want to have to just guess until we get the right answer. How you could use this guy to get that guy. Can you see any pattern?
Add 1 to the exponent and divide the coefficient by that.
That's pretty much it. Zoe nailed it. You add 1 to the power and then divide by the new power. See how that works. If I gave you 15x to the 4, you would add 1 to the power and then divide by that new power. Now, if that works, shouldn't this guy's derivative be him? Well, we know how to find the derivative. Don't you go 5 times 3 is 15? That works. And what do you do in the power rule? Well, after you multiply, don't you reduce the power by 1? And you see that works. So I'm going to write that down as a generic formula. If I give you any multiple of a power, like 5x cubed or 7x squared, let's call it ax to the n. Then what Zoe said was, you add 1 to the power, and then you divide by that new power. And this is called the power rule for integration. It's not called the power rule for finding antiderivatives, although it is. We tend to use the word integration rather than antiderivative. And there's kind of, well, when you do 152, you'll find that those two terms for a while are used at the same time. And then after a while, we just throw that word out and we use this word instead. So if somebody says integrate something, they mean find the antiderivative. And the process is called integration rather than what, anti-differentiation. It's a bit of a tongue twister, that. Maybe that's the reason we use integration. But it's not 100% correct. I'll give you an example of why what I've just written up there is not 100% correct. Suppose we took 6x squared, right? That's my function. Then its antiderivative function is 2x cubed. And I can check that. Isn't the derivative of this him? So I know that part works. Here's the problem. Don't all of those functions, when you differentiate them, don't all of them get you 6x squared? Because what happens to the +1 or the +10 or the -23? When you differentiate, don't these terms disappear? Right, they become 0. So when we talk about the antiderivative, right, we want to write it down so that we take care of that. So what you do is you add a guy called C. It even has a name. It's called the arbitrary constant. And what that guy is representing is the fact that we don't know what the constant term would have been that generated the answer. So every single one of these and now it's 100% right. So whenever you find an antiderivative, will you please remember to do the +c at the end? And it seems trivial, but it needs to be there or you haven't answered it fully. And for some reason I can't explain, WebAssign puts the C at the beginning. So when you look at the answers in WebAssign, it says C plus 2x cubed. I have no idea why they want the C there. Nobody that I know of ever does that. I'm 99% sure that if you write it this way around, it's happy. So it shouldn't be a problem. But just in case you get it wrong and you see the C at the front and you might think it's significant. It is not significant. It's just for some reason what WebAssign decided. Are we comfortable with our first group of antiderivatives? These are essentially polynomials, right? So if I give you a polynomial, we should be able to use the power rule for integration on it and find its antiderivative. So how about 7x cubed take away 2x squared plus 4x minus 3. And underneath, I'll do its antiderivative. And yep, I've decided to give you ugly numbers instead of nice round one now. So, you essentially take care of each one independent of the others. Okay, what would 7x cubed get you? Well, you add 1 to the power, and then you divide by the new power. So do you see you get a slightly ugly 7/4? Next one. What would x squared get you? Add 1 to the power,
Can
and
I
then divide
interrupt
by
for a
the new
second?
power.
I have a question.
Sure.
Is that f of x
Yes.
supposed to be the derivative of f above this? I thought we were doing this with the derivative, but we're not, right?
We are. Well, you're bigger than me, I'm smaller than you. It's perspective. You can phrase it from either perspective. If they are phrasing it, and it's quite common, but not totally common, they're saying, make this the original function, and we are finding the antiderivative. So we're finding a function that if I differentiated this, you'd get that.
Oh, okay, I get it.
So what I'm writing down is a big function that if it was differentiated would get me back to the start. Okay, so 4x. What does 4x become? Well, if you imagine that there's a 1 there, you add 1 to the power, and then you divide by the new power, so you get 2x squared. And lastly, what does the number -3 get us? The antiderivative of -3.
Wouldn't it just be a C?
Be negative 3x.
Yeah. And then you get your C that you wanted. So the C is there, it's just there. Any number, any constant like 5, its antiderivative is 5x. But think backwards. What's the derivative of 5x? 5. What's the antiderivative of 5? 5x. Do you see that perspective thing? You're bigger than me, I'm smaller than you, right? It just depends on which way you want to look at it. So the antiderivative of a number is the same number with an x attached to it. Technically speaking, I could still make that a power rule. Yeah, a bit weird, but I could do it. Couldn't you think of 3x as 3x to the power of 0? Add 1 to the power, you get x. Divide by 1, you still get the same number you started with. I prefer just to take numbers and stick an x at the end because it's easier to remember. Do we like polynomials? And we find antiderivatives of polynomials. Right, here's one for you. Okay, you got a minute. If you know what to do, it shouldn't take you any longer. Find that guy's antiderivative. Okay, let's go for it. I'll take a volunteer. Anybody feel brave enough to try the luck?
10 eighths x to the 8th minus x to the 6th plus 3/2 x to the x squared plus minus x plus c.
And I would say you nailed it, except for one. I'm being fiddly, but it's still points, so you have to do it. Is there anything you want to change?
Oh, 5/4.
There we go. Nailed it. So the process of finding antiderivatives of polynomials involves using a thing called the power rule for integration. I just think of it the way Zoe said it. Add 1 to the power and then divide by the new power. I mean, saying it to me, my brain, that just makes it easier to do. So let's show you what that would look like in website. Right. We want to find the antiderivative of that guy, 3x squared plus 7x, add the c. Pretty quick, right? I know there are a lot of questions, but half of them are actually as quick as that one. Imagine doing that one. Okay. Add 1 to the power, divide by the new power. Add 1 to the power, divide by new power. Okay. Let's start with that one then. Doing here. No. What you think you would do if someone said, find the antiderivative of that guy? It's the first time you've seen a question that looked like that. How do you think I'm going to tackle find the antiderivative of this function?
Should we multiply it out first?
That's what I would do. And then just use the power rule, right? The power rule for integration. And so the antiderivative, capital F of x, add 1 to the power, divide by the new power, add 1 to the power, divide by the new power. When you have a number, just stick an x at the end and finish with a plus c. That's how quick it should be. Add 1 to the power and divide by the new power. Let's move on to radicals then. I would like to find the antiderivative of 6 square root of x. The way I would approach it is to rewrite it as a fractional power. Isn't that what I would be doing if I wanted to differentiate f of x, right? I'd also write it as a fractional power. And then some good news. The power rule for integration works even when the power is a fraction, as it is in this case. And the power rule says, add 1 to the power and divide by the new power. So antiderivative is add 1 to the power. No, we don't call it 1.5. We call it 3/2. Right? We don't like 1.5 in math, right? We like improper fractions, or as I call them, top heavy. Now, add 1 to the power and then divide by the new power. So you have to get a little bit creative here. Isn't dividing by 3/2 the same as multiplying by 2/3? Right? Dividing by 3/2 is the same thing as multiplying by 2/3. So 2/3 of that guy gets you 4. Are you happy with that process? Now, we haven't really needed to, but now we do. There is style points. And for antiderivatives, at least as far as you're concerned, the style points are very limited. Just make it look like the original. So since the original had a square root, make your answer have a square root. Not much of a style point, but it's important to make things look the way everybody wants them to be, right? The same way. How about fractional power? Technically, that's a radical. It's just written as a fractional power. Add 1 to the power and divide by the new power. Let's see what it looks like. What would you get if you added 1 to 3/4?
7
7
quarters.
So you're doing a little mental arithmetic here. Say again?
7 quarters.
Okay. Now, instead of dividing by 7/4, can I just flip that round and say multiply by 4/7? Right? Now, multiplying by 4/7 does not get you a pretty answer, but it's the right answer. Now, do I need to turn this into the 4th root of x to the 7, or is this style points good?
It looks the same.
So that's the question. Shall I leave it alone or turn it into the 7th power of the 4th root?
I think you leave it alone because it looks like the original.
That's it. So your style points is just as long as it looks like the original. If the original is some weird, yucky fraction, then leave it as a weird, yucky fraction. How about this one? I want to find the antiderivative of 4, the cube root of x squared. To be able to use the power rule for integration, I will need to convert this into a fractional power. Okay, what's the cube root of x squared as a fractional power?
2/3.
And now I can do the antiderivative. If you add 1 to the power, you get 5/3. Instead of dividing by 5/3, you multiply by 3/5. And then don't forget your plus C. Are we good with radicals? Because the only kind of radicals you're going to get are square roots of this and cube roots of that, right? Or x to the 5/7, right? You won't see yet anything uglier than those types of situations. Are we good? Do you need to see more of them, or do you feel comfortable with the radicals? Isn't it still a rule for integration, right? Now, next one on my list is rationals. Interesting. We are not talking major fractions here, right? Rationals are fractions, right? We are talking quite limited scope here. Only certain kinds of fractions are we going to deal with. And this is one of the situations. So we're going to deal with things like 10 over x cubed and 5 over x squared, right? Things like that. And then we'll get a little bit trickier after that. I want to use the power rule, but I can't use it when it looks like that. Even if I wanted to, don't. It doesn't work. How could I rewrite 10 over x cubed as a power of x?
10 to the x minus 3.
Are you all happy with fractions become negative powers? Because we've used that algebra for other reasons. Now, this rule over here didn't say n has to be positive like x cubed, right? It didn't say it had to be positive because you could use square roots, half powers. It doesn't even say it can't be negatives because it is. Here is the power rule. Add 1 to the power. Yes, it is -2. Because I have been known to do -4 when I'm not being careful, right? Add 1 to the power is -2. And divide by that new power. And then don't forget your C. And style points. Make it look like the original. Does that question make sense? How we had tackled that rational? Try another one. Right, this one's a little bit sneakier, but it's still technically a fraction, so it's a rational. What do you think I'm going to do?
Would you write it as
Well,
4 times x to the -1/2?
you would, you nailed it. Have you noticed that every single question becomes, can I find a way to write it as a power of x? A negative power, a fractional power, or even a negative fractional power. But can I find a way to write it as a power of x? Because if the answer to that is yes, then you can use the power rule on it. And we like the power rule because it's add 1 to the power and then divide by the new power. Let's see what the antiderivative looks like then. If you add 1 to -1/2, you now get +1/2. If you divide by 1/2, isn't it the same as multiplying by 2? Right, reciprocal. So that's where the 8 came from, and then you add C. And then you have to say, is there any style points? And the question had a square root in it, so my answer should have a square root in it. Did that surprise you that the antiderivative of this thing was actually not even a fraction anymore? Because most of the time, don't fractions just get you other fractions? Which is kind of what you would think would happen all the time, but not all fractions. Antiderivatives end up being fractions. Now, if I was doing this and I wanted to check it, couldn't I just say, okay, if you started with this function, I would turn it into that guy. And then if I differentiated it, wouldn't I multiply by 1/2? And that would get me 4. And then wouldn't I subtract 1? And that would get me that. It works. Do you see that the power rule for integration works? How about this problem? That's a fraction. But I can't do the power rule on it because it's not single powers of x's. It's a whole load of things on the top over an x squared in the bottom. And I'm not allowed to say, oh, I'll just do the power rule to everybody and that's the answer. It doesn't work, right? You don't get the right answer if you did that. Any suggestions for what I might do to change this so that we can use the power rule for integration?
Multiply the top by x to the power of -2.
Do you remember? Oh, I don't know. I think it was about week 3. Totally different question, but can you remember when we had to try and find ways of differentiating this guy? You know, before we learnt about quotient rules and all that. Wasn't the strategy to do that? Remember we did that for the same kind of reason? Well, strangely enough, or maybe not strangely enough, it works quite well. That's 4x. Okay, the one that might play with your brain a little bit is, what do you get if you take -2x squared and you multiply it by x to the -2? What does that combination become?
Two?
Yeah.
-2.
Yeah, I knew that's what you meant. Now, that guy is ready to go, isn't he? That's ready for the power rule for integration. So its antiderivative is add 1 to the power, divide by new power. When you get a number, I just stick an x at the end. Add 1 to the power, and then divide by the new power. Let's see. And for style points, we got that. And I'm quite happy with that as an answer. And I hope whoever signed would be happy with that as an answer. But it might not be. And it might have that. Are you okay with how come these 3 guys became that one ugly fraction? Can you see what I did to make that happen? Are we good with these guys? Some nods, which I like to see. So let's just nip over to the homework and see what their questions look like. Okay. We did a guy not dissimilar to 5. Can you see that's just a power rule with some ugly fractions? If I was doing question 7, wouldn't I have to turn this first one into x to the half and this second one into x to the 1/3, and then I could do the power rule? Oh, I didn't do that one. I did do one like 8, like 9, sorry. Okay, did do one like 9. But I didn't do one like 8. What do you think you may have to do in question 8 before you try and do any antiderivative stuff?
Change the square
Get rid of
roots
that
to
square
1
root.
half.
Yeah, so turn all the square roots into halves. And do you see that square in the bottom? Wouldn't you probably call that t to the -1/2 and then just distribute it all? Do you want to see that one, or is it enough just to talk about it? Do you want to see me doing it?
I'd like to see that one. Yeah.
Okay, let's set that one up. You give me a few seconds. I'm just wanting to write the question down before I switch over, or I might lose the window and forget what it said. So we're essentially doing a radical, right? A fraction function. It just happens to have square roots in it, you know, as if that wasn't bad enough. So what I would do is call the square roots t to the half, and then take that guy, multiply through by negative a half. You know, if that was t cubed, I'd multiply by t to the negative 3. Now I'm going to take each one in turn. If you multiply these two together, you get 2t to the half. You multiply the 2 in the middle together, you get negative 4t to the negative a half. And the weird one is that if you multiply this guy and this guy, you just get the number negative 5. So I haven't done any antiderivatives yet. I've just rearranged it into a format that's going to allow me to use the power rule. Are we okay with that?
Can I ask a question really quickly?
Go for it.
Where did the negative sign on the 5 come from?
Did you all catch that deliberate mistake? Does any of you believe that that was a deliberate mistake?
I'm gonna say
It
that
was-
yeah, you throw these little tidbits in here to make sure.
No, I don't. I wish I could. But I normally actually tell you that I'm going to do it before I do it. So no, that anytime I do that, I think by now you should know that I can't count as well. You know, so it's not uncommon for 3 times 2 to turn into a 5 if I'm being careless. So it's always a good idea when you read over my notes to say, I think he probably meant to write plus there. So it's not a weird piece of math, it's just he made the mistake. Well, now I'm ready for antiderivatives. Add 1 to the power and then divide by that new power. Add 1 to the power and divide by a half, is like multiplying by 2. Numbers get you that, and finish with a C and style points. Now there is a very good chance that WebAssign will accept the answer that you can see. I want you to ignore the fact that WebAssign will do that, and will you just get into the habit of doing style points. It just makes the world so much easier when everybody has the same answer. And my phrase called style points is that process. Get it to a format that's typically considered the best form. And for antiderivatives, the best form is make it look like the original, right? That's all you need to worry about right now. Are we cool? So I am going to throw a fraction and sometimes the simplest questions will throw you for a loop. We've used the power rule for integration for tons and tons of different things, and every single time it's came through for us, right? It's found the antiderivative. It's been great. We've figured out that we can do it with square roots and 1 over x cubes and all sorts of cool stuff, right? And the power rule has never failed us. It's about to fail us. This guy should be written like that, right? If you're going to do a power rule, you have to write it as a power, right? Would you agree 1 over x is x to the negative 1? And I am about to attempt the power rule. I will add 1 to the power. Do you think dividing by 0 is a good idea? Can you see that the power rule doesn't work? I mean, it gives us an answer that's impossible, right? You can't, that there is just So what on earth is the antiderivative of this guy? There must be a function, right? That if I differentiated it, I would get 1 over x. And yes, there is. But you just have to know it. Who is what function do you need to start with to get 1 over x as its derivative? And you know this function.
The natural log of x.
Right. Isn't the derivative of the natural log of x 1 over x? So that is the only exception to the power rule not working. Right? 5 over x, 10 over x, or 1 over x. Anything that's just over an x, will you take that as a special case and remember that its antiderivative is the natural log of x. And how do I know that? Because don't I know what the derivative of log x is? Isn't it 1 over x? So I'm just saying, yeah, I know the answer because I've seen it before. Are we okay with that special case? Everybody else is okay, but 1 over x or 10 over x, that's going to cause you trouble. Okay, I don't want to waste our time, so I want to keep going. Let's do exponentials. In particular, let's do e to the x first. I love e to the x. In calculus, e to the x is your friend. What do you think the antiderivative of 7e to the x is going to be?
Would it be 7e to the x?
Isn't it a nice function? It's such a cool function. It's almost like no matter what you do to it, it doesn't seem to change much. Can you imagine then why e to the x is so loved and why we even have an e, why that special base is so important, right? Because it does so many cool things. There's not an awful lot of different questions I can give you. Couldn't I give you 2e to the x and minus 5e to the x, but wouldn't the answers be 2e to the x and minus 5e to the x? So that's kind of the exponentials done. Now one that's going to cause trouble. Nothing to do with the power rule. Don't do power rule. Nothing to do with that. It's really just a matter of working backwards. If I differentiated 2 to the power of x, right? So forget antiderivatives there. If I differentiated 2 to the power of x, wouldn't the answer be 2 to the power of x times the natural log of 2? Remember differentiating. What do you think the antiderivative of 2 to the x is? Well, it's 2 to the x, and it does have a natural log of 2 in it. But if you're thinking of it as the opposite process, where do you think you stick the natural log of 2?
Would it be dividing it by log of 2x?
And that is exactly what you did. So in general, if you want to find the antiderivative of e to the power of x, if you want to find the antiderivative of e to the power of x, the answer will be e to the power of x, not multiplied by the natural log of a, but divided by the natural log of a. Does that seem reasonable, thinking of antiderivative as the opposite or undo process of differentiation? We have learnt some cool stuff today. Come on. Have we, West, have we learnt some cool stuff today?
Yeah, we have.
Right. That's